Hello everyone. Today we will continue discussing together the uh, N-channel and P-channel MOSFET DC analysis. So just quick refresh for what we have discussed for in the previous class. So in the previous class we discussed these slides. So we discussed together the different shapes of MOSFET, the P-channel and the N-channel MOSFETs. And we described that for the P-channel MOSFET, instead of having P-type material, we have N-type material. And since we have N-type material, we will have two P or concentration of holes in the N-type material here, which is going to make now a P-channel in this place. And this P-channel will allow a current to flow in the circuit between source and drain. And regarding the biasing of this type of semiconductor switches, VGS gate is going to be negative compared to source, and VDS still drain is connected here to negative, and source is connected to positive, so it's opposite to the N channel one. But instead of saying V DS in negative sign, we will say VSD instead. And the same is also for VGS. Instead of saying VGS in positive sign, we will say VSG in positive sign. So let's replace the notation instead of replacing the signs of these voltages. So this is now the P-channel MOSFET, and we discussed the different modes of operation as well. So we said in the equations, you will have VSG instead of VGS. And regarding the threshold volt, we mentioned that the threshold volt is going to be in a negative sign. So the equation here, it's in positive. So when you substitute by the value, it will be minus. And here for the VSD, it's VSD instead of VDS, as we mentioned. So these are the same mode of operations we have like in N-channel 1. So we have the linear mode, the saturation mode, and the cutoff mode. And for the conduction parameter, instead of Kn in N-type material, or sorry, N-type or N-channel MOSFET, we have Kp, and in Kp, instead of mu n, the charge mobility or electromobility, we have the hole mobility mu p. So these are the differences between N-channel and P-channel in terms of the mathematical model and the operation. And regarding the symbols as well, we discussed the symbols of the two types of the MOSFETs. Also, we discussed the non-ideal case if we assume that we have slope and we have resistance for our MOSFET. So this means our saturation is not going to be like a flat curve. You have slope for this curve, and this will be intersect at a certain negative value here called VA, and the exact relation if you did not neglect this resistance R node. So in this case, the value of lambda will be considered, and we mentioned that lambda is going to be a very small value. So if you neglect lambda VDS, so the relation will be multiplied times 1, which is our equations we discussed recently. And we mentioned that the variable RO, we will call it output resistance. Output resistance may not be very clear to you now. Why we call it output resistance? It will be more clear when we discuss the AC analysis of our MOSFET. This is expected to be after like 3 classes from now. And we discussed what the meaning of the DC analysis. So again, DC analysis of a MOSFET means we need to identify the Q point, the operating point of the MOSFET. What the meaning of operating points? The operating point means the point that the MOSFET is gonna work. So today, after finishing these materials, we will start in another material and we will discuss some applications for the MOSFET and you will understand more about the Q points. So we will have different applications and we have operating point, which is the intersection between the load line and the characteristic. So we discussed up till now only the characteristic of the MOSFET, but there will be an operating point, and at this operating point, you need to identify some values. So firstly, the first type of analysis we discussed is the DC analysis. And we said the DC analysis, you need to identify the value of ID, and we will call it IDQ. And also identify the value of V drain to source, and we call it VDSQ. And Q is referred to the operating point. How can we make the DC analysis? We said that we have 3 steps. The first step is according to the circuit we have here. So this is here the common source MOSFET. The source is connected to ground. The drain is connected to VDD by means of RD. And you have 2 resistances, R1 and R2. It's act as a voltage divider to VDD in order to obtain the value of VG, which is equal to VGS, since source is connected to ground. So VG is the same as VGS. The steps, 3 steps. The first step is getting VG. How can we get VG? Use the voltage divider rule here to get VG by means of VDD. So once you get the value of VGS, you can now calculate and compare to see. Sorry, not compare to see. Next step is use VG in order to calculate the value of ID. How can we calculate the value of ID? Actually, we will start firstly with the basic equation of the MOSFET, which is the relation between ID and IQ. Sorry, ID and VDS, but we don't know which mode of operation. We don't know yet what is the mode of operation of our MOSFET. So in order to do the second step, we have to assume a certain mode of operation. We agreed together the easiest way is to start assuming the saturation operation. So the saturation relation is easier. So firstly, we will assume the mode is saturation and use the relation of the ID equals Kn times VGS minus VTN square. This is the relation between ID and VDS in saturation mode. And after getting the value of VGS from this relation, so the next step is to compare, sorry, after getting ID, use the third step, which is getting VDS from the circuit here. So from the circuit, we can write the relation VDS equal VDD minus ID RD, and then compare VDS. Compare VDS with what? With the VDS saturation. So you know that VDS saturation equals VGS minus V threshold. So VGS is calculated in the first step. Subtract VGS minus VTN. So you will know the value of VD saturation. Compare the VDS saturation with the VDS you obtain from step number 3. If the V drain to source you calculated is greater than the VDS saturation, which means in our characteristic, if this is our characteristic like that, and this is the transition between linear and saturation, this is ID, and this is VDS. So this is the value of VDS saturation. If the value of VDS is greater than VDS saturation, so this means you are working in this operating region, which is the saturation region, and in this case, your assumption is correct. If not, if the value of V drain to source is less than VDS saturation, so in this case, you have to repeat from step number 2 again, use the linear relation to get the value of ID, and then calculate VDS from the circuit by the same equation number 3. Also, we solved last class some or one of the examples here, and we compared the three steps we just discussed, and we figured out in this case here the assumption was correct. And I asked you guys to solve this quick assignment. Today we will continue the same analysis, solving more examples, but the first thing here is going to be in P channel MOSFET, not N channel MOSFET, just to let you know how to deal with the different types of MOSFETs. So how can we make the DC analysis for a P channel MOSFET? So by the same way, here, this is our drain. This is our source. Sorry, this is our source. This is our drain. So in this case, guys, we can call this as the it's not common source like what we have in the N channel, but here the source is connected to VDD. The source is connected to VDD. So here in this example, it's considered VDD, and maybe in another textbook you may find it VSS, whatever the name of this supply. It's not a big deal, but just a symbol. But the source is connected to the positive volt, and the drain is connected to ground through a resistor RD. Now, what do we need to do is we need firstly to calculate the three steps. So follow the three steps of the DC analysis. So the first step was calculating VGS. So as you can see here, guys, VGS is the voltage between gate and source, but here it's going to be VSG as we mentioned. So it's opposite now. So the S is here. This is S. This is G. So VSG positive is here and negative here. And if you compare that, you will find that it's equivalent to the voltage drop across this resistance R1. So if I would like to get it, how can I get this volt? I can use now the voltage divider rule and get the volt across R1. So I can say VG, this point, firstly equals VDD times R1 divide R1 plus R2. So this is the voltage divider rule. And again, guys, we all of the time, we will assume that the IG equals 0. This is all of the time the gate current of a MOSFET in a steady state equals 0. So when we start making the analysis of the MOSFET and see how to trigger or how to turn on a MOSFET using pulses and see the current of the MOSFET. So there will be a current, yes, but this is to turn the current on, so to turn the MOSFET on firstly, okay, and then the current decay to 0. So once you turn on the current, the DC steady state current is going to be 0 of this MOSFET, okay, but you will have VGS all of the time if the MOSFET is connected or working either in saturation or linear mode. So there will be a value of VGS all the time and IG equals 0. So since IG equals 0, we can apply the voltage divider rule. So the volt of this point equals, if I would like to get the volt of this point compared to ground, so I can apply R2 divide R1 plus R2. So I can say VG equals R2 divide R1 plus R2 times VDD. So this is going to be now the volt of the point VG compared to ground, but I need to get the volt across the resistance R1, which is the same as the voltage drop between gate and source, or SG. So in this case, we need to say VDD minus VG. Okay, so this is the way, guys. Okay, so this is the first step. So this is now step number 1. Step number 2 is substituting in the relation, the MOSFET relation, not the circuit relation. So the MOSFET relation, we will assume also the operating mode. So the step here says, assuming that VGS is less than VTP, or if you neglect the sign, or take the absolute value of the VTP, so it's going to be positive. So we can say VSG is greater than VTP. So VSG as a number, whatever the sign now, or let's say in general, VSG or VGS absolute value. So we can say, or write it in a different way. If VGS absolute value is greater than VTP absolute value. So the number, whatever the sign, okay? If the number is greater than VTP, so this means now the device is going to be biased, and the device is going to be on, okay? And we need to have it greater than the VDS saturation, okay? Sorry, guys, this is here. There is a mathematical error. This shouldn't be like that. So the relation should be if VGS minus VTP greater than VDS saturation. So the same condition we have. So there is a typo in this equation. So this is the correct condition again. So in this case, we can say it's in the saturation region, and we can apply the relation of the saturation. So ID equals Kp times VSG minus plus VTP square. And take care that again, VTP is going to be negative value. So substitute and get the value of ID and use the circuit relation. According to the circuit relation here, guys, we can say now VDD equals VSD plus IDRD. So in order to get VSD, let me write the equation again. VDD equals VSD plus ID times RD. In order to get the VSD, move this in the left-hand side, IDRD in the left-hand side. So the relation number 3 is VSD equals VDD minus IDRD. Get the value of VSD. Get the value of VSD. And yeah, this is the correct condition, guys, that I mentioned. So please, as I said, this is incorrect here. Okay, this is type. So if VSD is greater than VSD saturation, which means equals to VSG plus VTP, so then the transistor is in the saturation region. However, if VSD is less than VSD saturation, so in this case, we can say the transistor is in non-saturation, or let's say linear region, and we have to repeat the calculation using the relation of ID in the linear mode. So the same concept, just changing the signs and the equations according to the p-channel MOSFET. Let's start solving, guys, this example together. So in this example here, we need to calculate the drain current and source to drain volt. And this is again the meaning of DC analysis. So I need to get I drain and VSD. And again, guys, don't forget that these are capital letters. Why capital letters? Because we are making DC analysis. And according our discussion before, if I go back a few slides, just to remind you that the Fourier series is summation of DC component and AC component. The instantaneous is all of the time little letters like that. So V of omega t, I of omega t like that. And the DC component is capital letter all of the time, and the AC component is the remainder part. So AC component is uh, expressed as sinusoidal part. So it's going to be V maximum sine omega 1 t or omega t, 2 omega t, 3 omega t's for all the different frequencies. So this is Fourier series. I think you already learned that, or most probably will learn that in other classes. So again, don't forget that we are using capital letters here. So we need to calculate the Q point values, ID and VSD, where voltage of common source circuit with P-channel enhancement mode MOSFET. So the same is still common source, guys, but the source is connected to a volt magnitude, not to ground. Okay, so still the circuit have the same name, common source, but the source is connected to the volt of the 5 volt here, not to ground. Okay, now we have VDD given 5 volt, and the values are assumed here in this circuit to be R1 equals R2 equals 50K, VDD equals 5 volt, RD equals 7.5 kilo ohms, and the VTP is minus 0.8 volt. As we mentioned, guys, it's going to be in a minus sign. Okay, so this is the transistor threshold volt. And Kp equals 0.2 milliampere per V square. Let's do the analysis together. We need to make 3 steps. First step, as we mentioned, you need to calculate the value of VSG. Let me write this here. So step number 1, calculate VSG. Step number 2, calculate ID with the assumption of saturation. Firstly, number 3, use the circuit equation to get VSD and compare. Compare with what? Compare with the transition point, transition of the saturation. So these are the 3 steps we need to do in order to get the correct values of ID and VSD with these parameters. With these parameters means if we change these parameters, guys, this is going to change the operating mode for sure. Okay, and later on we will discuss how to design a circuit to fulfill a certain operating mode, to select a certain operating mode. Okay, let's start with the first step again now. So we need to get VSG. So how can we get VSG? So VSG is the volt between or the volt across this resistance here, and we can get the volt across this resistance as we mentioned, guys. So VG equals R2 divide R1 plus R2, which is times VDD, which is 50 divide the resistance was here. Both are 50 kilo ohms, so 50 plus 50 again, times VDD equals 5, so this is 2.5 volt. Now, we need to get VSG, so VSG equals VDD minus VG. So it would be 2.5 volt as well. Someone can say, why we didn't use from the beginning R1 divide R1 plus R2 times VDD. It's correct. If you would like to do that, I 100% agree with you. But the textbook here, guys, just would like to unify the equations. So he unified here the equations in case of P channel and N channel. So he used all of the time to get this volt firstly. So he made a constant relation for Vg, which is R2 divide R1 plus R2 times VDD. However, if you would like to get the volt across this distance, which is equal to VSG, and I 100% agree, and I like it actually, so it will make it just in one step. So for sure, you can say R1 divide R1 plus R2 times VDD will provide you with the value of the volt across this resistance. You can call it directly VSG. You can call it directly, this is VSG. I will write it here in the notes if you would like to make it in one step instead of that. So I can say here, guys, VSG equals R1 divide R1 plus R2 times VDD. Because by the end, it's just voltage divider rule. Okay. So if you would like to use this equation, this is okay. If you would like to use the textbook equation in order to unify the relation between P and N, it's up to you. Okay. But I'm fine with both. Okay. So this is the first step. So I'm going to write this is now step number 1. Step number 2, let's assume the operation in the saturation region. So we will use the saturation equation here. So ID equals Kp times VSG plus VTP square. So Kp is given 0.2 milliampere per V square, and VSG is calculated 2.5 volt, and VTP is minus 0.8. So don't forget to make the minus sign. So 0.8, and the value here is going to be 0.578 milliampere. So this is now the drain current. Are we now in the saturation or not? We don't know. We need firstly to check the value of VSD. So use the circuit equation. How to get the VSD from the circuit equation? So VSD equals VDD minus ID times RD. So 5 minus ID that we already calculated here times 7.5 kilo ohms. So the volt is 0.665 volt. So this is VSD. In order to check now, we need to compare with the value of VSD saturation. What's the value of VSD saturation? Actually, it's nothing but VSG plus VTP. So VSG is 2.5, as we could see here. And VTP is minus 0.8. So 2.5 minus 0.8, it's 1.7 volt. So now 1.7 volt means our case is not achieved, because as you can see, VSD is less than VSD saturation, which means our transistor now is working in the linear mode, not in the saturation mode. And this doesn't mean that this volt is correct. This means our assumption is incorrect. So we have to repeat everything again. So starting from the step number 2 and calculate ID with the linear relation. Now it's more steps. Let's see this together. So firstly, ID equals Kp constant, 2 VSG. VSG is unknown. VTP is given. VSD is unknown. Sorry, VSG is calculated 2.5. VTP is unknown. VSD is unknown. VSD square is unknown. So when you substitute here, guys, in this relation, here, when you substitute here in this relation, it will be a quadratic equation. And this quadratic equation has two unknowns. What are the two unknowns? ID is unknown, VSD is unknown. So how can we solve this? We need to solve two equations together. If we have two unknowns, so we have to solve two equations. So the first equation is our current equation. So this is the first equation. Let's say this is equation number one. And here, the second equation can be obtained from the circuit. How can we get it from the circuit? Simply, the equation from the circuit is VSD equals VDD minus ID times RD. Now, let's substitute with the value of VSD in our equation. So this will go here and here as well. So this is going to be now relatively complex equation. Okay. But this is a way to solve uh, analytically this technique. We have another technique, guys, but this is graphical way. It may not be easy to be discussed here, but we may elaborate more about this technique when we start in the design procedure. Now, let's substitute in our equation with numbers. So these are the numbers we have now, and the equation will have just one unknown, but it's still quadratic equation. So if you solve this quadratic equation, you will get two values. In the textbook here, he solved only one value. And let's continue. You will see his comment here, why he mentioned only one value. Actually, because the other value is not going to achieve the condition. So he got two values of ID, and he substituted with the two values of ID in the equation of VSD equals 5 minus 7.5 times ID, which is VSD equals VDD minus RD times ID. So after getting two values of ID, substitute in this equation, you will get two values of VSD. Again, he selected just one value here and he gave this value only. Why? You will understand that after finishing this part. So he said that VSD is going to be 1.14. If you compare now 1.14, it will be less than the VSD saturation. So you remember that VSD saturation is calculated 1.7 volt. So it's less than the VSD saturation, which means this assumption is acceptable. Actually, the other assumption will provide a VSD greater than 1.7, which means it's not acceptable because we 100% sure that the transistor now is working in linear mode. For that, guys, we do not start the assumption in linear mode. Why? Because the linear mode assumption will provide a quadratic equation and you will have two solutions. The two solutions, one of them will be in the saturation or maybe in the saturation and the other may be in the linear. So how can you guarantee now what solution is correct? We don't know. So this is the procedure. We have to start firstly with the saturation assumption because the saturation equation has a first order equation, just linear first order equation. So just substitute it and get the values and you will be sure that which operating mode you are operating your transistor. So this is the way, guys. So here in the comment, in solving quadratic equation for ID, we find a second solution that yield that to VSD equal 2.93. For that, he didn't mention here. This is a textbook solution, guys. But for sure, in order to know that, you have to substitute with the two values. So I urge all of you guys, when you solve this equation, you should provide the two values. So I'm expecting that you will get ID1 and ID2, for instance. Then you will get VSD1 and VSD2, and the VSD2 will be here 2.93, and then you can say this is not accepted. Why? Because we are 100% sure that our transistor is working in the linear. So this is the best way to answer this question. Okay. So he mentioned here he didn't try this because we already know that the transistor is working in linear mode. So having 2.93 greater than the VSD saturation, which means it would be in the saturation region, is not possible in this case or with this circuit, because we already checked this solution before and it's not working. Okay. Nice. So this is, guys, how to solve the equation. This is how to make the DC analysis for a P-channel MOSFET. And like what we made in the N-channel MOSFET, I gave you a quick assignment for the N-channel MOSFET. It's not uploaded yet on eCampus. I will write the quick assignment on eCampus, but I will combine the two problems together. The first N-channel question, quick assignment, and this second question. So you need to solve both in the quick assignment. So this will be added to quick assignment. Okay, nice. So this is the remainder parts of the previous materials we started on Tuesday. And here in this material, we learned the N-channel and P-channel MOSFET operations, the samples of both of types, and the DC analysis of MOSFET. Now, I will share with you these materials for sure. Let's start in the new material, which is related to MOSFET load line and load drive circuits. What the meaning of load line and load drive? We will not uh, reach to the load drive, I believe, today, but we will start with the load line. What the meaning of load line? So let's see, guys, what we have here in this material. So in this material, guys, we will discuss it today and in the next class. And next class is not in the coming week. So the coming week, first class will be for the exam. So we don't have class on Tuesday. And Friday is the full break, I believe. So there is no classes in the coming week, and there is no lab also because we have exam. The exam will be available on eCampus. You can turn it in, or let's say not turn it in. You can make the exam because it's gonna be online. You can make it any time during the 48 hours on Monday or Tuesday, and the exam is going to be multiple choice and fill in blank. It will include some numerical problems. So you need to answer everything on eCampus, even the numerical problem. You need to write the final answer on eCampus. And after you finish, you have to submit the exam. If you didn't finish the exam within the time, it will be submitted automatically. Okay, but it may make some problems for you if you didn't write the numbers or everything. So beside that, after you finish the exam, I will give you 10 minutes immediately after submitting the exam to submit a handwriting solution for the numerical problems in order to have the steps written for your numerical problem. So this is the plan. So next week, the coming week, we will not have classes. We will have just exam, and then we have the full break. So let's start, guys, now with the design. So the concept of the load line, we will understand the concept of the load line by means of design. What do we mean by design? So design, I will have a certain transistor, and I need to control the operation or the operating point of this transistor. So this is the design. For instance, assume that this is our MOSFET. The potential or the voltage of this point is VD, which is the drain. The potential of this point is Vs, which is the source. Here we have a resistance between source and a supply, another resistance between drain and another supply, and here we have a gate resistance connected to ground. So this is a circuit, and let's see exactly what do we need to design here. So in this example, or in this circuit, the objective is to design a MOSFET circuit biased with both positive and negative voltage. So we have positive and negative voltages at S and D to meet a set of specifications. What are the set of specifications? This is the meaning of design. So I need to have a certain value of ID and VDs. So let's say this is N-channel MOSFET, so I need to have a certain ID, and I will call it IDQ, which is the operating current, and VDSQ, the drain to source volt of the operating point. So I need to have a certain value for these two parameters, which means by the end, if this is my characteristic, this is I drain, this is V drain to source, and this is, for instance, the characteristic at different VGS, VGS1, VGS2, VGS3, and so on. So many characteristics we have, and this is what you can see in the datasheet. And then you need to achieve a certain operating point with V drain to source and I drain. Most probably, the value of ID and VDS will intersect one of the curves. So I'm gonna say this is the value of IDQ, and VSD, sorry, DSQ. So this is the Q point. So even if you don't have this characteristic in the data sheet, you can estimate the characteristic here like that. And this means now, guys, you have a certain operating point. So the certain operating point, guys, is going to be the intersection between what's called load line and characteristic. So this is the load line now. So this is a certain value of ID. We will see what is the equivalent equation of this value. And also this is another certain value for V drain to source, what the equivalent value of this VDS in terms of other parameters. You will see that in the design. And this is our Q point. So the idea is design in order to achieve a certain operating point on the ID VDS characteristic. And then this Q point, guys, you will learn how to control this Q point to go in this side or in that side in order to control the mode of operation of your MOSFET. Also, how can you control this point to go in this side or in that side? So in every place, how can you move the load line itself to move in this direction or in that direction? Okay, so all of these are design process, and all of these depends on the values that we will use to make the design. Like what? Like the value of RD, value of RS, and two other values, guys, which will control the VG. It's not exist here in this circuit for this example, but later on you will see like R1 and R2 in the previous examples. Okay, so we will see this together. But for this circuit, for the time being, we need to achieve a certain drain current and drain to source volt. So here it has been mentioned, guys, standard resistor are to be used. Since this is going to be design problem, so you have to use standard values. It's not allowed to use a value, for instance, for a resistance not existing in the market. So you have to use standard values of resistors in your circuit. And he also mentioned that a transistor with nominal parameters K prime N equals 80 microampere per V square, and omega over L equals 6.25, and V threshold equals 1.2. So these are the parameters we have, and we need to design this circuit to achieve ID and VDS. Let's see, guys. We don't have no more equation, guy. We don't have any new equations. So just the MOSFET equations, saturation or linear, and the circuit equations. Circuit equation, it's gonna be vary according to the circuit design we have. So we can write the circuit equation. I think now all of you guys are expert in electrical circuit. You can write Kirchhoff circuits easily, and this is what we will do in the design problems. So let's see, guys. Starting firstly with assuming that transistor imbies in the saturation region. So this is the normal assumption we start with. So we have the relation which is ID equals Kn times VGS minus VTN square. But here he said IDQ because by the end this is going to be the Q point of our design. Let me change the color again. Yeah. So this is going to be the Q point of our design. So we didn't mention, guys, before what is Kn prime. Maybe it was not exist before. So what is Kn prime? Actually, this is the relation between Kn and Kn prime. So the parameter Kn equals Kn prime divide 2 times omega divide L. So Kn prime is given. So we will just divide this over 2 times omega divide L, which is the channel width divide the channel length. So the value of Kn is 0.25. So this is now the value of Kn we have in our problem. In order to solve this equation now, you have K, you need ID, VGS can be calculated, VTN is given, so we can write our equation now. VGS equals root. From here, we can get VGS as a function of ID. So it's going to be IDQ divide Kn under root 2 plus VTN. ID is given 0.5 milliampere. So go back one step. we mentioned that we have ID equals 0.5 and VDS equals 4 volt. VGS was not given. So we can say VGS equals IDQ divide Kn under root 2 plus under square root of 2 plus VTN. So this is now 0.5 divided 0.25, the Kn, plus 1.2 volt VTN. So we got VGS equal 2.614. In the design process, having VGS means you know now which curve you are working on. Let's go back one slide. So having the value of VGS, this means you will know which curve of the datasheet you are going to use. Because in any datasheet, guys, you will have many curves. I'm not sure if I got a chance to show you the datasheet in the class, but for sure in the lab, we will see this together. Let me show you a quick example for a MOSFET datasheet. So again, guys, in order to find any let's type any type of MOSFET. Wolfspeed is one of the well-known companies providing the silicon carbide MOSFETs. So let's grab any of these MOSFETs here. So I'd like to show you any, yeah. So let's see, is it a discrete? Okay, so this is a discrete MOSFET. Can you see here, guys? You have gate, SSS, and D is most probably from the other. The D is the heat sink itself of the die. Okay, so the all of that is considered as D, and here we have the S. So this is a like special design of a die of MOSFET. Okay, it's called bare die. Okay, so this is different to the three-terminal discrete switches. You may know. Let me show you something like more familiar. You'll be maybe more familiar with. Yeah, discrete MOSFET, for instance. Okay, let's open this one. Yeah, okay. So here we have, guys, the three terminals discrete MOSFET. So this case style is TO247 3 pins. So this is very well-known shape for the MOSFETs. Okay. And this is a symbol we have here. And as we mentioned together, guys, before that, any MOSFET will have its anti-parallel diode inside. So this is called anti-parallel diode. And I would like to show you the characteristic of the MOSFET. So can you see, guys, here? This is the drain to source volt. This is the current. But this is, as you can see, this is like in a very short period, up to 10 volt only. But the overall characteristic would have higher voltages. It's not exist here, the full characteristic of this MOSFET. So as you can see, guys, this MOSFET can work up to 700 volt here. And in the beginning of the data sheet, let me go to the beginning here. So this MOSFET actually is, where is the data here? It's N-channel enhancement mode MOSFET. This is the same like what we are discussing right now. And the V drain to source is 650 volts. So the maximum is 650 volt here. So we're supposed to see the characteristic up to 650 volt, but he focused on some of the characteristics and he didn't provide the full range of the characteristic here. It's supposed to given, okay, but this is not complete data sheet. Okay, here it's a bit wider range. Uh, so as you can see here, guys, this is the first part of the curve. This is the first part of the curve. It's not giving the part of the saturation right here. Okay. So now we know the value of VGS. Getting VGS again means we know now which curve on the data sheet we are working. We still need to get the resistors. So if we go back to the circuits, we have the value of VG, VG to VS. So this is what we got now. We got the value of VGS. So this is a gate to source volt. So on the MOSFET, this is G and this is S. So we have this volt between these 2 points. We still need to get more data in order to calculate the remainder parts. So regarding the resistor RS, we can say, guys, let me grab the circuit here in front of us. So RS, this resistance here, we can say this resistance equals the volt Vs minus the volt V negative divide the current which is flowing here, which is ID, because we have the value of ID already. So we can say Vs minus V minus or minus V negative divide ID equals RS. So what the current flowing in this branch, guys? Yes, correct. Your thinking is right. IG equals 0. So what the voltage drop across this resistance since this current is 0? So since this current is 0, this means the voltage across this resistance is 0 as well, which means this volt equals 0, correct? So we don't have voltage here right now. VG equals 0. And you have VGS. So we can say VGS equals VG minus VS. So 2.614 equals VG, which is 0, minus VS. So we can say VS equals minus 0.641 or sorry 14. 614. Okay, we can substitute now with the value of Vs here. So Vs equal minus 2.614 minus the negative, which is minus 5, divide our current, which is zero point 0.5 ampere. So the value is going to be now here minus minus is going to be plus. So plus 5 minus 2.6 divide 0.5. So the value of Rs is going to be 4.77 kilo ohm. So we got this resistance now. Now we have RD. We need to get the value of RD. How can we get the value of RD? VDS is given. So if we go back one slide, VDS is 4 volt. So we have this volt here is 4 volt. So you can write a Kirchhoff for this loop here, which is V plus or plus 5 volt equals IDRD, ID is given, plus 4 volt plus IDRS, RS is calculated, minus 5. So this is the loop here. So this is the next step. So we can say VD equals VS plus VDS. Or this is another way. So he calculated here in the textbook, he calculated from this point only. You know the potential of this one? Okay. So he said VD equals VS plus VDS. VD, the drain volt, equals VS plus VDS because you know that VDS equals VD minus VS. And you already have VS. So you can say now VD equals VDS plus VS. So VD is, sorry, VDS is 4 volt. This is given. Plus Vs equals, we just said it's 2 minus 2.614. So from this point, guys, we got the potential volt at point D. So Vd became a known value. So this volt now is known. So we can say this Rd equals 5 volt minus Vd divide Id. Okay. If you feel like this way is not convenient to you, you can write the complete loop equation because I know in electrical circuits you use to get like the complete branch equation. It's fine. I'm gonna write the complete branch equation to you here. If you would like to solve by this way, this is fine. If you would like to follow the textbook solution, it's fine. So I'm gonna say now the equation, or let's say loop 2. Let's say this is loop number 2 or Kirchhoff number 2. So I'm going to say V plus equals RD ID plus VDS plus RSID plus V negative. So this is the equation. Now you can substitute. RD is unknown times ID equals 0.5 plus V drain to source equals 4 plus RS is calculated 4.77. So 4.77 kilo times 0.5 milliampere plus V minus is given minus 5, so minus 5. So you will have also one equation, and V plus is given plus 5 volt. So you will have one equation and one unknown, which is RD. So you can get RD from here. So this is another way. It may be simple to you because you used an electrical circuit to make a complete Kirchhoff or loop like that. But if you would like to consider the volt of a certain point, it's up to you. So both of solutions are acceptable. Okay. So this is the textbook solution now, guys. He considered the potential volt of point VD from the potential volt of the point Vs or point S, and he got the value of Vd, and then he used the uh, just one small part of the Kirchhoff, which is Rd equals V plus minus Vd divide IdQ in order to get the value of Rd. So the value of Rd by calculation is 7.23 kilo ohms. Now, we may note that our drain to source 4 volt is greater than V drain to saturation, which is VGS minus VTN, which means our uh, assumptions was correct. And from the beginning, to be honest with you, having VDS equals plus 4 most probably for small power MOSFETs, this is going to be in saturation region because the V drain to source or the characteristic is going to move from the linear to saturation in very small value of V drain to source voltages. Okay, so 4 volt is large enough to operate the MOSFETs or most of low power MOSFETs in saturation mode. Okay, so now we got the values of RD and RS, and this is the design requirements here in this question. Trade-off, take care that the values we got may not be available in the market. So what we should do, 4.77 is not exist in industry, but you can find 4.7 kilo. So 4.7 is available. And also for the value of RD, 7.23 is not available. So you can find 7.5K. Does it mean our circuit's is not gonna work? No. But what you can do is you can just check. Check what? Check the values of these resistors with the same values of supply. What will happen to your ID and VDS? So if we assume now using these values of resistors, substitute in the relations, you will find that. For instance, VGS plus IDRS minus 5 equals 0. So this is from the circuit. Okay, VGS, let me grab the circuit here again to be close to you. So here we have VGS, which is this volt here, plus ID times RS plus this volt here equals or minus 5 equals 0. So he got the loop from this point to that point. Okay, where ID equals Kn times VGS minus VTN square. What we can do is simply let's recalculate. So recalculating means let's calculate VGS. According to the value, according to the value we have here, so IDQ is gonna be 0.506. So repeat the calculation, guys, again. So ID is gonna be 0.506, and originally it was zero point 0.5. So you have like 6 uh, micro, or let's say point no 60 yeah 6 micro, 6 microampere error, okay, which is very acceptable, okay. And also VDS is 3.83 instead of 4. It's a bit little compared to what we need. However, in design, guys, it's not going to be very complicated like that. Why? Because simply you can control your drain, or VDD and VSS. So instead of having -5, I can change this value in order to reach to the desired value of ID that I need. So your supply is going to control that. Okay. So this is a concept in the design. So for the second part here in the trade-off, I'm not 100% agree with the textbook in this part, because by the end you will control your values of the supply in order to achieve the required current after your design. So you can tune your supply in order to do that. Okay. Uh, yeah, here he has another comment, guys. It's important to keep in mind that current into gate terminal is 0 in this case. Then the 0 voltage drop across RG is 0. And this is clear in our solution in the discussion we have. Okay, so this is, guys, our load line now. I think we can uh, uh, delay the load line discussion to the next class, because time is due now. The class time is due. So let's start next class, guys, from this point, from the load line and MOSFET operation at the operating point. So again, I just would like to remind all of you that midterm exam is going to be available for 48 hours on Monday, this Monday and Tuesday. Any time you can log into your eCampus. Once you started the exam, you have to continue the exam. It's not allowed to close it and open it again. It will not be accepted. Once you finish the exam, submit the handwriting solution you have, and next we will continue our classes after the fall break. Thank you so much, guys, and I wish you the best in the midterm exam. Have a nice evening.